Okay, so the last lesson, we talked about the law of iterated expectations. Sometimes has the funny abbreviation LIE. Law of iterated expectations ain't no lie. And let's remind ourselves what that tells us. It's says that the expectation over Y of the expectation of X conditional on Y is just the expectation of X, the unconditional expectation. Okay, so when we iterate this expectation through an intervening conditioning variable, we just get the same expected value as we started with. So that's pretty cool. You might be thinking that things always get a little more complicated when we talk about variances. And right, that's going to happen here too. So you might be wondering, what about the variance of the conditional mean? Or for that matter, the expected value of the conditional variance. What about those things? Well, they do have a somewhat complicated relationship to the unconditional variance. The unconditional variance, it turns out, is the sum of these two things. So it's, I wouldn't say it's actually not complicated. Complicated is the wrong word. It's not obvious that would be true, but it is. And so let's write that down. So that is indeed the law of total variance right here in our title, and sometimes abbreviated LTV. So what that says is that the variance of X, the unconditional variance, is equal to the expected value of the conditional variance. Am I getting the, I think I have one too many parentheses here. Plus the variance of the conditional expectation. Okay, let's think about what those things mean. Okay, so this actually does have an intuitive interpretation. Let me sort of maybe work towards that this thing, the expected value of the variance of X conditional on Y. I'm just writing that out. Expected value of the conditional variance. We think about this as the expected variation within a group that's defined by Y. This word within comes up a lot. Defined by values of Y. Okay, so in those different values that Y can take, how much uncertainty do we expect there to be within those different groups? Or how uncertain about X do we expect to be if we know Y? Okay, got a little more to say about that, but let's kind of interpret the other term kind of along these same lines here. Okay, so this is the variance of the conditional mean. It is the variation across values of Y. and it is how different are expectations about X for different values of Y. Okay, so the law of total variance sometimes is called like variance decomposition. So the way people think about it is we're breaking down the observed variance in X in terms of what can be explained looking across values of Y and what is going on within groups of Y. So a place where this gets applied is in education. When people look at test scores, okay? So we might be looking at how much of the variation in students' test scores is across different schools and how much is within different schools over a whole sample, okay? So this across and within separation is what makes this kind of complicated relationship. I said complicated again, and it's not. It is complicated. I think I'll just stop apologizing for it. It's in one sense it is just a sum, and I guess that's why I want to say it's not complicated. But the two things we're summing up are complicated: the expected value of a conditional variance and the variance of a conditional expected value. And I would say this is one of the places where I may be sort of like pushing the limits of what you would normally do in a class like 200A. So I kind of want to keep your stress levels at not too high. Here, this is kind of advanced stuff. I want to show it to you now because if you see it now, it'll be easier to wrap your brain around when you see it again. And you will see it again, and you're going to have chances beyond this quarter to become comfortable with it. And it is worth becoming comfortable with because this question of how much variation goes on within the value of a conditioning variable. So, you know, how ignorant do we expect to be about X once we know Y? If this is a big number, what it's saying is that knowing Y doesn't really help us that much. There's still we still expect to have a lot of variance among our X's. And over here, this is the variance across values of Y. And if this is a greater portion of the total variance, what it's saying is, oh yeah, knowing Y really helps us a lot. So I'm going to proceed with this in two steps. I'm going to, the next page, derive this guy. Okay, that, and I would say, you know, if you're feeling like this is just a lot, you want to skip the derivation, it's okay. You can skip it. It'll be there some other time. You can come back to it. That's going to be the end of this video. In the next video, though, I just want to sort of walk through an example parsing out these two things. And I think that example will be, will make it more concrete. All right. But let's go ahead and let's look at that derivation that I have copied here because it is such an exercise in managing these all these different parentheses. Okay. So what I'm doing here over the 7 steps is starting with just our standard formula for the variance of X as the expectation of X minus X squared. And I'm going to get to the end, law of total variance, that it decomposes into the expected conditional variance plus the variance of the conditional expected value. So just going through the steps here. The first thing I'm doing in this step is I've got my variance formula. And what I'm doing something kind of weird. I'm using the law of iterated expectations kind of in reverse. Usually what you do is you have something complicated like this, like the expected value of X squared conditional on Y. And look at that, I've already got a missing set of parentheses. Let me correct that with a slightly thinner line here. Okay, so I guess it's okay without those parentheses. All right, so we've got x squared, and I'm just substituting this whole thing, the expectation over y of the expectation of x conditional on y. Okay, usually the law of iterated expectations would say we'd go from this to the simple thing. What I'm saying, when I'm saying we're doing it in reverse here, we're going for the simple thing and replacing it with the iterated expectation. Okay, so this is just our expectation, unconditional expectation of x squared. And over here, I've got the expectation over y over the conditional expectation. So it's just the law of iterated expectations. And then I'm doing exactly the same thing, clean this up here on the other side as well. Okay. So here, inside the parentheses that are being squared, I've just got the expectation of x. What is that? It's the iterated expectation of x. Why am I doing that? Because it's the standard. Let's make these things complicated, recombine them, and then derive the finding that makes sense for us. So that's the first step. For the second step here, I'm just focusing on this one term. Okay, so this isn't like a continuation where everything's equal to the line before it. Here, I'm just taking this one term, and actually really all I'm taking is the inside of it here, just what's on the inside. Okay. So let's look at that. And okay, so that's the expectation of the square of x conditional on y. And what I'm doing here is I'm just applying the standard variance formula, but in kind of an unusual way, like again, kind of a reverse way. The usual variance formula is that the variance of, we'll apply it to an x squared here, the variance of x conditional on y is the expected value of x squared conditional on y minus the expected value of x conditional on y all squared. Okay. So it's the variance is the expectation of the square minus the square of the expectation. That's our standard thing. We've made it conditional here. We're conditioning on y throughout, and then we're moving this term to one side. And actually what we're doing is we're adding this term to both sides. So that is the variance formula. So now we're taking what we did in step 3, we're taking what we did in step 2, and what I've got here in pink, I'm just substituting what we found it to be equal to. So the things that we're working with are big and complex, but it's still just sort of basic algebra here, because all these complicated things really are just numbers. Okay, so combined them. Okay, so now we're looking at what we've got. So we've got the expectation of y of this sum, and we know that the expected value of any sum is a sum of the expected values. So all I'm doing here is I'm taking this expectation and applying it to both terms. Okay, so I've got this term plus the expectation of this term. And throughout all of this, this final part is just kind of coming along for the ride. We're not doing anything to it. Okay. Until we get to step 5. And now we're going to leave the first term alone and do some things to the second term. And I'm going to do that same trick that I did in the last video of substitute, just give this expected value of X conditional on Y, give it its own name to help me sort of see it as a single thing and not think about where it came from. So I'm just defining this and substituting here. So there's my expectation of X conditional on Y. Here's my Z, they're both squared. Here's my expectation of that thing. Here's my expectation of Z. So just doing that substitution. And when I look at it this way, now this lets me see, oh, what is that? Look at that. That's the expected value. I'm sorry, it's not the expected value, it's the variance of Z, right? It's the expectation of Z squared minus the square of the expectation. Okay, so this is the variance. Haha. And indeed, that's how I rewrite it. Now I'm actually done. Now all I have to do is substitute back. What was Z again? Oh, it was the expectation of X conditional on Y, and this is indeed my formula. Okay. So it's really not a lot of steps. It is a lot of parentheses. That's I think that's a hard thing about it. And the terms that we're moving around are big and complicated. As I said, is this sort of the level of derivation that I think 200A students should be able to do on their own? No, it's not. Watching this, do I hope that you see that this law of total variance does make sense in the same way that all of our other things have made sense, that it's been derived kind of in the same way as the variance formula, the covariance formula, the rule about the sum of the expected value of a sum, all of those things, okay, that it is derivable. The steps are maybe at a little higher level than we're used to, but we get this interesting result. And to give you a more concrete look at this interesting result, I'll see you in the next video.